Okay, here we're going to start learning about probability, a very important concept that is very, very applicable to everyday life and situations. We're going to start with the idea of an experiment. It's an activity with observable results. Don't think chemistry when you hear the word experiment. So often we move to that. But it's just any activity where we can record and observe the results. If it's an experiment that doesn't always give the same result, even under the same conditions, it's called a random experiment. And repetitions of an experiment we call trials. Here's some examples. Rolling a dice, even under the same conditions, you would not expect to get the same result every time. Drawing a card or a name out of a hat. Counting the number of defective radios in a sample. In probability theory, we usually, when we use the word experiment, we mean random experiment. We can make a list of outcomes of the experiment. Now, sometimes there may be a lot of them, and we may just describe the set of outcomes rather than listing them all separately. But each outcome is called a simple event. In each trial, one and only one simple event will occur. In other words, the simple events are broken down as much as possible. The set of all such simple events or outcomes is called the sample space. Subsets of the sample space we call an event. And if that event has more than one element in it, we call it a compound event. If our event is the empty set, remember the empty set is a subset of every set. So if we're going to call the subsets of the sample space an event, we have to allow for the possibility of it being the empty set. If it is, then we call it an impossible event. If our event is the entire sample space, then it's a certain event. Let's do some examples, and we're going to set up the sample spaces. Okay, if we roll a single six-sided die, okay, so our sample space, then we'll indicate it. We're going to call it with a capital S. We want to list all the possible outcomes of this experiment. Well, what possible things can come up? 1, 2, 3, 4, 5, or 6. This is the most obvious and intuitive sample space. You could come up with others. For example, your sample space could be odd number, even number. That's certainly a possibility. This is more descriptive of the experiment, though, because it says what exact things can happen. If we spin a roulette wheel, which has the integers 0 to 36 on it, our sample space then will be the set of integers 0 to 36, and here's a case where you wouldn't write them all out specifically, but we're going to write out enough to describe the pattern. We're going to count the integers all the way up to 36. Okay, let's suppose we have a manager of a local theater who is recording the number of customers that attend a particular movie. The theater can seat up to 500 people. What's an appropriate sample space for this experiment? Well, you want to think, okay, what is the experiment? The manager is recording the number of patrons. So what we need to write down, what are all the possible numbers of patrons that he could record? Well, what's the smallest possible number he could record? Very unpopular movie, unpopular time, no one comes. He could record 0 if no one came. 1, 2, 3, 4. Okay, what's the most he could record? Up to 500, because that's the maximum capacity of the theater. So there's our sample space. Now let's describe the event that fewer than 50 people attend the movie. So we're going to call this E for event. You could choose any letter you like. It's a subset, so we're going to use set notation. We're going to use our brackets. Fewer than 50 people. So 0 would qualify, 1 would qualify, 2 would qualify, all the way up to, what's the very biggest number that would qualify? Fewer than 50, so 49, right? Okay, let's describe the event that the theater is more than half full at the movie. Okay, well, what would be exactly half full? 250. We want more than half full, so the smallest number that would qualify would be 251. 252, 253, all the way up to, where would we stop? The maximum possible number, which would be 500. Well, we're 499, 500. Okay, let's move on. Let's suppose we have an experiment that consists of studying the composition of a 3-child family. And we want to write down an appropriate sample space for the experiment if we're interested in the genders of the children in the order of their births. Okay, so perhaps you could just write it down. We need to have some kind of a shorthand that says the order and the gender. So let's let B represent boys, and let's G represent girls. So we're going to make up a little shorthand. And one thing you could do is draw a little tree. So for the first child, what could happen? You could either have a girl or you could have a boy, right? And then for the second child, what could you have? A girl or a boy, a girl or a boy. And then you could go on to the third child. Girl or boy, girl or boy, girl or boy, girl or boy. Okay, and so in this case, if we kind of run along the branches, girl, 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 we could do girl, girl, girl. Here, girl, girl, boy. Third branch, girl, boy, girl, and so on. And here we would do boy, girl, girl. And we'll keep on. Let's go ahead and write down our sample space. So this would be our answer for A. Okay, girl, 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 boy, girl, boy, girl, girl, boy, boy. Now we move to the bottom half. Boy, girl, girl, boy, girl, boy, boy, girl, boy, like that. Boy, boy, girl. Boy, boy, boy. You could do this without the tree too. If you just notice, okay, let's do the all girls, let's do the all boys. Then you could figure out all the, if you wanted to do 2 girls and a boy, you could put the boy in either first, second, or third position. And then you could reverse it. So, but sometimes the tree is helpful. Okay, let's describe the event E, that there are 2 girls and a boy in the family. Okay. 2 girls and a boy. Okay, so hang on, let me make sure I have an equal sign in here. So we could have the boy in the third position. We could have the boy in the second position, or we could have the boy in the first position. Those are the only ways to get 2 girls and a boy. Okay, oldest child is a girl. Okay, we're going to call this set F. Okay, so oldest child, that would mean the way I have it listed as first. You could also do youngest to oldest, whatever your notation is. Okay, I'm listing the oldest or first child first. So the oldest child is a girl. So after that, I could have 2 girls, or I could have a girl and I could have a boy and a girl. I could have either the boy coming next, or I could have a boy and a girl, the girl coming next. Okay, and if you look back at your sample space, hang on, I forgot one. If the oldest child is a girl, what else could I have? I could have the oldest child a girl, but then I could have two boys following her. Girl, boy, boy. And if we look back at our sample space, girl, 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 here, girl with boy, girl in either order, and then a girl, two boys, and so on. Okay? The oldest child is a girl, and the youngest is a boy. Okay, so that means the girl has to come first, and the boy has to come last. Okay, what goes in the middle? Well, there's two options. Maybe the middle child's a girl, or maybe the middle child's a boy. Oldest child's a girl, youngest is a boy. I think those are all of our possibilities. Okay. Last, let's do a new sample space. I'll call it S2. Appropriate sample space if we only care about the number of girls and we do not care about the order. In other words, what are the possible outcomes? So now I don't want to have all this extra information about order. I want to have strictly the number of girls. So what are the possible numbers of girls that we can have in a 3-child family? Well, we could have 0 girls. We could have 1 girl. We could have 2 girls. Or we could have 3 girls. Are there any other possibilities? I can't think of any. I certainly can't have 4 girls in a 3-child family. The most I can possibly have is 3. Okay, let's move on. Okay, here we're going to roll a pair of dice, and we want to figure out what the most useful sample space is. And this is not going to be the only sample space, but it's going to be the sample space that contains the most information. And then after we get the sample space, we're going to write down some various events. Okay, so we want to start with the sample space. So if we roll a pair of dice, and you can actually visualize, like let's suppose you have 2 dice, and one of them's blue and one of them's green, and you throw them. Okay, well each of them could still come up 1, 2, 3, 4, 5, 6, right? But the numbers could be switched between the blue and the green dice, and you have to take that into account when you write down your sample space. So what we're going to do is we're going to come up with ordered pairs, and we're going to call this to be the first die and this to be the second. And keep in mind that you could think of the blue one as being first and the green as being second. But of course, whether the dice are 2 different colors should be irrelevant to our problem. It's just a way to visualize and realize that if we switch the order, we actually have a different outcome. Okay, so even if we throw them both at once, we can still think of them as first die and second die and write their numbers in ordered pairs. Okay, so if the first or the blue die comes up, let's just write, and you know what, I'm going to make really big curly brackets like this, and you're going to see why in a minute. Okay, so first one comes up 1. What are the possibilities for the second die? Well, it could be a 1, or it could be a 2, or it could be a 3. All of these we still have 1 on the first or the blue die. Could get a 4. Could get a 5. Could get a 6. Okay, those are some possibilities, right? What else could happen? Well, on the first, these are all the things that can happen if our first or our blue die happens to be a 1. Okay, now let's suppose the first or the blue die happens to be a 2. What are the possibilities? Well, second die could be a 1. Second die could be a 2. Second die could be a 3. Second die could be a 4. It could be a 5. Or it could be a 6. Okay. Third die. Same thing, right? Okay. So all the way up to 3, 6. Okay, so I wrote down a bunch of them, but now we're not going to write down all of them because I think there's enough here that you can see the pattern. Okay, so we could put a 3 on the first die, and then the other could vary between all the numbers. We could have a 4 on the first die. And then all the second numbers could vary. We could have a 5 on the first die. We could have a 6 on the first die. And then we could have a 2 on the second, 3 on the second, 4 on the second, 5 or 6 on the second. Okay, and you see the pattern here? So I'm going to put some little dots to indicate we're going to continue in that same pattern. And I'm going to put brackets around the whole thing. Like that. Here's our sample space. How many are in the sample space? Got 6 across, 6 down. It looks to me like there are 36 elements in our sample space. Here's the way that we say this. The number of elements in the sample space is 36. Okay, so now let's write down our events. Okay. The sum is 6. Let's call this set event A. We want to write down all the ones that have a sum of 6. Okay, so try to be systematic about it. Let's start with the first coordinate or first die being 1. What can I put with that to get 6? 1, 5. Okay, now if 1, 5 is a possibility, 5, 1 is a possibility. In other words, maybe the blue die is 1, green is 5, or you could have the blue being 5, green is 1. Those both give me a total of 6. How else can I get a 6? Well, I could have 2 on that first die, in which case the second one would have 4. And then I could switch the order. Or I could have 3 on the first die, in which case, what's on the second? 3. Would I switch the order there? No, because what does this mean? Both the blue and the green die get a 3. Hey, there's only one way that can happen. Okay? So these are the order pairs that are in the event where the sum is 6. Those are the only ones. Okay, let's suppose our sum is 2. What order pairs will let that happen? 1, 1. Is there anything else? Nope, that's the only way to get a sum of 2. Okay. Sum is more than 9. Okay, so here, if the sum is more than 9, what's it going to be? Well, 10, 11, 12. Is there anything bigger than 12? Is it possible to get a sum of 13? No, because our dies only go up to 1 through 6, right? So the maximum I can possibly get is 12. So here my event is going to be, okay, being systematic again, let's figure out how we can get 10. Start with 1. Can't do it. The other die won't go high enough. 2 won't work. 3 won't work. But what about 4? 4 will work because I can put a 6 with it to give me 10. And then I switch the order. So 4 will work, 4 and 6 will work. What else will work? 5, 5, which is only going to show up once. I don't need to change the order. Okay, now we get to a sum of 11. What are the only ways to do that? 5, 6, 6, 5. Okay, now how do I get a sum of 12? 6, 6. Any other possibilities? Nope, no other ways to get a sum of 9. So that's it. I hope that helped you get the feel for sample spaces and events.